Okay, so this lesson is on subtracting vectors. So in our last lesson, we looked at the method for how we add vectors. This particular lesson will be on now how we subtract vectors. Okay. In our last lesson, I did show you two different ways of how we could add vectors. One using a very mathematical approach with triangles, law of cosines, law of sines. Just again, keeping in mind that that really only works if you only have those two vectors and it makes a nice triangle. You would have seen in one of your examples, practice problems, that when you've got three or more vectors, you do have to use that idea of vector components. Okay, now we're going to focus a lot more on vector components in another lesson, but for today, when we're doing our subtracting vectors, I'm strictly going to stay with what we're most familiar with, and that is the triangles and law of sines, law of cosines stuff. Okay, so let's get into it. So for vector subtraction, again, it's just a method that's often used, again, in any sort of calculation in physics. Just like we need to add things, you need to be able to subtract things. A very common way to see it is when you're looking for the change in something, right? When you're trying to calculate change in, right, or delta, it's one thing minus another. Okay, so that's where this idea of vector subtraction is going to be coming into play a lot, right? So if you're looking for the change in velocity, you're looking for VF minus VI, and this is going to be a subtraction of vectors, not an addition. Okay, so that's the biggest spot where you're going to see it, right? You'll notice on this slide here, and this is going to come up a lot, is when we talk about a second vector or vector B. Okay, so we can show that this vector here is going, kind of up and to the right. The negative vector, okay, so negative b, is the same magnitude. It's got the same length, right? It's the same value, except it's going in the exact opposite direction. Okay, and that's going to be a key property when we talk about being able to, one, draw the diagrams of these, and two, be able to use them for calculations. Okay, so again, noting that a plus b is sorry, that should say a minus b. That's a typo. I'm going to actually edit that right now. Okay, noticing that a minus b is mathematically equivalent to a plus negative b. Okay, so we can really just use the same method of adding vectors with subtracting vectors, but just noting that when we go to draw that second vector, right, using that tip to tail method, we would draw it in the opposite direction. Same value, same magnitude, but in the opposite direction. Okay. So I am going to go, though, over the two different ways you can use the setup here for subtracting vectors. You can pick the one that kind of makes the most sense or works for you, but you should understand how both of them work and how they both give you the same answer. Okay. So method one is, again, considering that same method we've been using with adding vectors. We're using that idea of a tip to tail idea, right? So you draw your first vector, you then draw your second vector, right? So if you were doing vector A minus B, okay, we draw vector A, no problem. But then when we go to draw vector B in the tip to tail, it's adding the opposite, right? Because it's negative B. So we would still draw it with the same magnitude, but in the actually opposite direction. So if it had said like, it travels this many due east, we would draw it going due west. Okay, then once you've got both of the vectors drawn, you again draw your resultant vector from the tail of your first vector to the tip of your second vector, right? So it's again that look from the exact place you started to the exact spot you end up. And then you can measure the length or calculate the length and the angle of your resultant vector. Right. The other way you can do this in terms of subtracting vectors is draw vector A and draw a vector B in the exact method it's been laid out with you, but notice here that you're doing tail to tail. Okay, so you wouldn't be drawing vector B where the tail is attached to the tip of vector A. You would instead draw the tail of vector B and attach it to the tail of vector A instead, right? And then you again draw the resultant vector, and again it's a little bit, watch yourself with it. The resultant vector here goes from the tip of B going to the tip of A. Okay, so that's where that changes as well, right? And then measure the length or calculate the length and go from there. Okay, so we will all show you kind of both ways of how you'd at least draw this. Sorry. The calculations end up being the exact same. You end up drawing the exact same triangle. Again, I'll show you that here in a second. You end up drawing the exact same triangle, so the calculations don't change, right? You end up getting the exact same law of cosines values being used in that equation, and then you're done. Okay, so it's just how you decide to set it up and just being very careful with how you're setting that up. Okay, So these are all going to be right now just examples with velocity, right? Because that's the thing that we're most comfortable with. We haven't really talked about change in acceleration or anything like that, but it could be used in the exact same manner, right? But a change in velocity is, remember, Vf minus Vi. So that would mean when we're looking at a problem, they might give us Vi and they might give us Vf, but we have to kind of, they might give us Vi first and Vf second, but Vi is the vector that's being subtracted, so it would be considered vector B, okay? And then Vf would be what would be considered vector A, okay, to follow those steps. So let's just kind of get into that. We'll do 2 problems together as a group, or like I'll do 2 problems together on video. There'll be then 2 problems still in the notes for you to try on your own, plus an extra worksheet for you to attempt as well, okay? And then that'll be subtracting vectors. Okay. So let's go into our first sample problem. So problem number 1, we have that a jogger is walking briskly at a rate of 9 meters per second north. She then begins jogging, moving at a rate of 15 meters per second, 40 degrees north of east. Calculate her change in velocity. All right. So with this one, again, we start any problem like this, start with what we have, right? So what we've been given in the problem is that her initial velocity is 9.00 meters per second north, okay? We've also been given that Vf, right? She changes and her final velocity ends up being 15.0 meters per second at a direction of east 40 degrees north. Okay, I don't think the question actually said that. I think I just manipulated it because this is the way I prefer to write it. You might have said like 40 degrees north of east, but I prefer to write it like this. It's easier for me to see. Right, we've been asked for a change in velocity. Right? What is her change in velocity? Right, so using that triangle there for delta, right? So delta V, her change in velocity would be Vf minus Vi. So if we're gonna say, okay, well this is gonna be like using that example of A minus B, right? Well then this is vector A, Vf, and the Vi is vector B, okay? So again, we can look at this as 2 ways. We've got A minus B, okay? But remember that that's mathematically equivalent to A plus negative B, okay? So I will draw these in 2 ways. Okay, I'll have to erase the board and kind of do one at a time, right? But I am going to show you that you do get the same values. We get similar triangles here. Okay, so we'll start with like using the A plus negative B because that's like the addition of vectors, the same we did last class, so it's the most common. Okay, so we'll start with that. So the first diagram I would draw in this idea of A plus negative B is I would draw my vector A, right, which was the Vf. So that was the 15 meters per second at east 40 degrees north, okay? So if that's my bearings and I'm going east 40 degrees north, I'm going around this, right? And I know that that's a 40-degree angle in there, and that was at the 15 meters per second. Okay, so that was a value of 15 meters per second that way, okay? Now, if I'm adding negative B, okay, so I'm adding the opposite vector. So again, if we went back and we looked, we said, okay, well, the initial velocity was 9 meters per second going north. Well, the opposite of going north is going south, right? So if I'm going to be adding these, I'm still going tip to tail. So from where that tip is, I'm now going straight south at that 9 meters per second, right? But now I'm going straight south because it's the opposite direction, right? So it gave me 9 meters per second north, but I'm now drawing it 9 meters per second going south, okay? Because it's adding the opposite, all right? And then my resultant vector would have been the same during my addition, where it's from the tip of the beginning to the tail of the last one. So it would have been my resultant vector would have been here, okay? And I'll just kind of erase that. So that 40 degrees is actually not inside the triangle. What might help is knowing that that would have been a 50, okay? Because this is now, right, so this, it's a little bit north, right, because that would have been going straight across that way, but this is now my resultant vector going a little bit north, okay, but just by off, right, so the 40 degrees is the entire thing, so whatever this is different okay, is what we're kind of looking for. So that would be if we were drawing it using the a plus negative b. If we were just going to draw it using a minus b, and we used kind of the second idea, it's again drawing your first vector as it is, right? So it's that same, okay, I'm going east 40 degrees north, so I did this, right? And that value is at your 15 meters per second. And then you're going, okay, well, my first vector, b, right, so a minus b, is the 9 meters per second going north. But in this case, because I'm not adding the opposite, I'm just showing you using the straight subtraction, I still go 9 meters per second going north, but I do tail to tail. So I do this instead. Okay? And then again, so like this is a here, this is b here. So before, when we were adding, we always went, okay, well, this is my original starting point with A, and then this is where I end up over with B. But your resultant vector here doesn't go A to B, it actually goes B to A. Okay? So it looks like it's, my diagram is going to be a little bit off. I should extend this just a smidge, okay, to make my point. So my resultant vector actually does this. Okay, so again, you see that those are similar triangles going, right, the entire resultant is still going north and a little bit east. And you'll see that they're actually similar once we fill in that angle, right? Because we're going to solve this, we need to know what this angle is here. Okay, so just basic alternate interior angles here, if we went do, right, it's kind of like your Z theorem here. This angle is the same as this angle in here, right, because this is the same north-south line, north-south line. So this north-south runs parallel with this north-south, so do, and then that 50 is the same as that 50, right? So what you get is a triangle. It's an SAS triangle, so 15, 90, and the 50s in between, so there's only one way to stick this value here. And if you notice, the same kind of thing happens here, was this was drawn at east 40 degrees north, so that was 40 degrees. This line is going straight north, so that leaves no choice for this angle to also be a 50-degree angle. And once again, you get that same, okay, well, you got two sides, 9 and 15, two sides, 9 and 15, 50-degree angle in the middle, boom, boom. These are the exact same triangles. One's just pointed down and one's just pointed up. Okay, so you'll get the same value by doing law of cosines, right? And you'll end up getting the same angle, right? So this one will be, you know, we can probably calculate this and then subtract it, or in this one, you'd have to kind of do a little bit more thinking. Just pick the one that works for you, okay? So at this point, we're ready to mathematically figure everything out, right? So this is essentially what we're figuring out. This is our change in velocity, that length there. So it's just a matter of setting up our law of cosines, right? So that would be delta V squared is equal to our 15 meters per second squared plus 9 meters per second squared minus 2 times 15 times the 9 times the cosine of 50 degrees. Okay, you plug all that in, you get that that value squared is equal to 132.447. And that would technically be meters squared per second squared, right? Because that's meters per second, you square it, it's meters squared over second squared, you're adding it to the same thing, so you still get meters squared over second squared. This is, again, meters per second times meters per second. That's just a constant, that's just a constant. So your units are there, then you square root, and you square root that and that, and you just get meters per second. Okay, so once you square root that, you get an idea of 11.5, and we do get 3 sig figs, I think, here. So 11.5 meters per second is the value, and now it's just a matter of figuring out, well, what is going to be my angle here. Okay, so I like this triangle better. That's just a personal preference. Because what I can do here is I can figure out, well, what is this angle here, right? And then all I need to do is, knowing that the 40 was from here all the way down to the bottom, right? And then what I can figure is, okay, well, if all of that was 40, I can subtract that angle and get what this little angle is in between here, right? What's that I'm going for? Okay, so that's how I'm going to tackle this one. So I would do that now using law of sines, because I have enough work for that. Okay, so now I'm looking for that. So sine theta over 9 is equal to, this is my pair that I now have, so sine 50 over my 11.5. Okay, multiply both sides by 9, and you get sine theta is equal to 0.5991. All right, sine inverse that, and you get that theta is equal to 36.8 degrees. Okay, so like I said, that angle there is 36.8 degrees. This whole angle here was 40 if we're thinking going straight across east, which means the difference between that, right, the 40 degrees minus the 36.8 degrees, ends up giving me a value of just 3.2 degrees. Okay, so that means that this resultant vector here, doing this, went east, but 3.2 degrees north. So my entire change in velocity is 11.5 meters per second, east, 3.2 degrees north. Okay, so I started by going north, then I end up going an east 40 degrees north measurement, and my overall change velocity is an east 3.2 degrees north, right? Because from north, right, I've changed my velocity by a value of 3.2 degrees, okay, going in a new bearing direction. Okay, so that's example 1. Okay, so again, if you're looking at another full solution for that, I have included that there as well. Okay, and you kind of again see those two diagrams there. All right, we're going to do a second example together, and then I'll leave you for the other two because it's just kind of a lot more of the same. Okay, so if we look at this second example, what you've got is instead an airplane is flying en route to Ottawa, it travels 2.40 times 10 squared kilometers per hour, or 240 kilometers per hour, at a bearing of 35 degrees north of east, or east 35 degrees N, right, east 35 degrees north. And then it changes its course going 3.20 times 10 squared kilometers per hour, or 320 kilometers per hour, just east. Calculate the change in velocity. Okay, so same idea there, with first identifying, VI, VF, and what our vectors are. Okay, so we have that VI is equal to that 2.40 times 10 squared kilometers per hour at that bearing of east 35 degrees north, right? And if you like, you could just call that 240 for right now. Might help with your calculations, okay? It then changes to a velocity of 3.20 times 10 squared kilometers per hour going straight east. Okay, or again, you can think of that as 320, right? Because you move that decimal place twice there. 20 kilometers per hour. Okay, so since we're asked for the change in velocity, that's VF minus VI. Okay, so if we're thinking about that, it's A minus B, that means that this is vector A here, and this is vector B here. Okay. So again, you have two ways of setting this up. You can think of it as A minus B, and if you're using the A minus B, you're going tail to tail, or you can think of it as the change in velocity is A plus negative B, and at that point, you'd be able to set it up instead as the same ways we've been doing, like adding vectors, right, where it'd be tip to tail, and then what you'd end up being able to do is just figure out your resultant vector in the same way we've done the other one. Okay, so that's that's the other thing we could do. So let's again, I'll set up both. We'll again see the two similar triangles, and then we'll go from there. Okay, so I'll do those two sets again. Okay, so in the first method, if we were to do it with the A plus minus B, right, so kind of using the same idea of just adding vectors, but adding the opposite here, we'd start with our first value of A, so our VF, which was just straight 320 kilometers per hour going east, so that would be this, right? and then adding the opposite. So VI was at 240 kilometers per hour going east 35 degrees north, right? So if we thought about that, it would have been like east 35 degrees north going this way, right? But we're going the opposite of that, so we're instead going to go this way, right? And instead of going east 35 degrees north, we're instead going to go west 35 degrees south, right? So if that's my west line and that's my south line, I've gone west 35 degrees south here, okay? Because that would have been the east 35 degrees north here, and this is just, again, opposite angles, right? If these kind of made an X, right, opposite angles are the same, okay? So that's where we end up, right? Because we're adding the opposite. So instead of going east 35 degrees north, we're going west 35 degrees south, right? With that angle there is my 35 degrees, and then there's my 240 value. These are in kilometers per hour. Okay, so that was vector 1, vector 2, and then we did them tip to tail. So my resultant vector is this, right? And we're trying to figure out what's that value as well as like what's this angle in here so I can get a bearing on it. Okay, if instead I set it up using just the A minus B again, right, and we're doing subtraction and we'd be going tail to tail instead, okay, we would again set up our first vector A, right, so going 320, right, so that value is 320, straight east. We would still go in the same direction of the east 35 degrees north, but instead of starting from here, we're going to do tail, connected to the tail. So from there, right, that was straight east, so east 35 degrees north, going like that, and that's 240, and that's a 35 degree angle in there. But again, this time your resultant vector goes from B to A, so it went this way. Okay, so again, you get this exact same, well, they're similar triangles, right? You've got this SAS, there's only one way to draw an SAS triangle, because you've got 320, 240 with a 35 degree angle in the middle. That side length, right? 320, 240 with a 35 degree angle in the middle, that's going to have to be the same, okay? And then even if you look at how the resultant vectors are pointed, right, this is in general going a southeast direction, and same thing as southeast direction, and these angles would all end up having to be the same anyway because they are congruent triangles, okay? So again, this one's just kind of bigger, so I'll keep going with it. I can solve for my delta V, again, just using my law of cosines, okay? So delta V squared, the sum of the squares of the other two sides. So 320 squared plus the 240 squared minus 2 times 320 times 240 times cos of 35 degrees. You type all of that in your calculator, you get a value of 34,178.246. Right, and again, if you were thinking units, it's meters squared over second squared. You would square root that value, and you get an answer there of 184.87. Oh, sorry, these aren't meters per second, these are kilometers per hour. My bad. Okay, so there, and then we've got 3 sig figs to deal with, so I'm going to put that back in scientific notation the way that they had it, or we can just think of it as 185, right, or 1.85 times 10 squared, okay? So our change in velocity is 1.85 kilometers per hour, or 1.85 times 10 squared kilometers per hour. Okay, and now we need a direction to go with that. So what we need, like I mentioned already, is this angle in here. So again, you can just set up your nice law of sines here, where this is your pair, because now you have your delta V, you have that as that 185. Okay, so again, I just subtract this one over here, just to make space to do that sine law. Right, so we can set up that sine theta over 240 is equal to the sine 35 over the 185. Multiply both sides by 240. You get that sine theta is equal to 0.7441. Okay, go for your sine inverse, and you get that theta is equal to 48.1 degrees. Okay, and then that 48.1 was starting east and then going south, so the bearing you'd need to put on your final answer here is that east 48.1 degrees south. Okay, so that is subtracting vectors. Okay, so there's the answer for the first one that we just did. There's the full out answer for the second one we just did. And I've got 2 independent practice problems for you to take a look at. Right, so give these a try after your video. Maybe make sure you're okay with these 2 before you go into the worksheet for the additional practice problems. Okay, but again, this one similar idea, 1 and 2 are numbers 3 and 4 essentially at this point. The solutions are here in the video and in the slides. You can just pause and take a look at them. Right, so there's the answer to 3. And there's the working answer for 4. I had made the cardinal mistake and I did my stuff in pen, realized I had made some bad drawings and mistakes, so I had to just scratch that one. And I worked with the second triangle in this case because I made a mistake with the first one. Okay, so there's our value that we need to, that you get. Okay, so give those a try. Pause the video, take a look at those, or go into the slides and just download them and look at what those solutions are. Make sure you're okay with that. And I'll upload the worksheets. Again, I've got one worksheet where it's just practicing drawing, right? So either practicing drawing the adding plus the negative or doing the tail to tail, up to you how you want to do it. Right, just making sure you get comfortable with how to set them up. And then the other ones that are similar to what we've been doing, where you need to mathematically conclude all this stuff. Okay, so again, I've been kind of mentioning too that you could be doing this more graphically, right? If you had graph paper and a ruler and a protractor, and you could try and set all these up so that they worked out almost perfectly, and you just be measuring these values, right? That is a way that you can do that. And again, if we were in class, that's what I would have done as an introduction, and then showed you that the math works out pretty much the same as if we were just sketching and measuring with rulers and protractors. But we're a little bit trickier in this situation, so I just want you to kind of focus on the math stuff because we can confirm those a little bit easier. Okay, so that's it, and then you would do your practice problems with this, and then off we go. Okay.